very simple. So we had a cochain complex. Okay, then defined notion of cochain map is like in homological algebra. Then it is over some ground field, K in this case. Then we go to the cohomology of this guy, which is regarded as a cochain complex with zero differential. Then we want to construct a coisomorphism F between two. Then we can form another cochain complex by ground field itself with zero differential. Okay? Then we want to find a cochain map of this guy. Okay? So here, because F is a cochain map, dF must be 0, because it's 0 here. And C is a cochain map, so CD must be 0 around here. And then all those cochain map is defined up to homotopy. So both F and C are defined up to homotopy. Okay. And additional condition was F is a quasi-isomorphism. Okay, that is, if we make that construction, then we can compose F and C to go from cohomology to number. Okay, and here we really want to this guy, which is both we regard as a simple model for this, but should be equivalent. So that's why F must be quasi-isomorphism. Okay? Then it's extremely easy to see that CF is homotopy invariant. C composition F is invariant under homotopy. Okay, so that's how we produce number. So if you make this construction, an example of this construction, of course, all those integral theory and the computational period, that kind of thing is really just constructing this kind of homotopy invariant. Okay, so that is part of the story here. Now we may deal with start to throw in more structure, okay? Not just the cochain complex, but let's consider algebraic structure here, such that D is a derivation of product. Degree alpha times D beta. Okay? And this guy is differential graded algebra. Around here. Then we want to define notion of morphism of DJ by just respecting all those structures, and morphism must be cochain map because we have cochain complex, and morphism must be algebra map because we have algebra. Okay, here. But the problem is that that kind of notion of morphism does not well defined up to homotopy. If I change a map to homotopy, the new map, which is homotopic to original one, would no longer be an algebra map. Okay, so dF, so if I have W, K, D, and dot, or the saying, and dF is FD, and F is an algebra map, okay, but if I change F to something homotopic to F prime, so SD plus DS, where S is a map from B to W with degree -1, okay, then F prime is not an algebra map. So something is wrong, so we have to change category of DGA to something more flexible one, which localize well with respect to cochain homotopy. That's, I try to give them motivation around here. Then now, here's a simple question you can ask, okay? If f prime is not an algebra map, then what it is, okay? It is possible to construct a second map, which I call f2, which from B tensor B to W, okay? Which in terms of S and D. Okay, so we have, if I have homotopy, I can just make a map F2 such that F alpha times beta minus F alpha times F beta equal to D F2 alpha beta plus minus or something F2 D alpha beta plus minus F2 alpha D beta. So, let's say F prime, okay. F was satisfying that, and F prime satisfying that property. Using S and D and original F, okay, I can cook up something called F2, okay, which is bilinear map satisfying this property. So then we see, well, it's kind of okay because the failure of F prime being an algebra map is up to homotopy. It's D something, okay? So if you go to cohomology, this just becomes strictly algebra map. Okay. So you can regard this as a kind of consistency condition, okay? The first consistent condition. Then you have to worry about that how things behave, how F2 behave with respect to product, and so on. In that way, you can drive Fn, which is mapped from B tensor n to W, okay? And you can write down some natural equation, some natural thing of saying that. So some higher version of this thing. So then let's say F1 equal to F. Okay? So this idea is that if you change the notion of morphism up to homotopy, introduce this homotopy, then everything is okay. So instead of saying DJ is a strict morphism, you relax it by introducing this homotopy. Okay? So this sequence, which I call F, which is F1 to F2, okay, here is called A infinity morphism. Okay. So this is my introduction to A infinity morphism, A infinity algebra on here. So I'm not going to tell you what is the detailed formula because there exists well-defined notion which localize well up to homotopy. So you do learn some homotopy machine, then you can easily, maybe not easy, but you can construct this one there. Okay? Now, you can replace this structure, everything to the algebra picture. So change that to the bracket here. So then instead of DJ, we obtain DZA. Then the exactly same thing would happen. Then you'll find L infinity morphism. Okay. So both A infinity and L infinity morphism, now we want to have defined notion of quasi-isomorphism. And simply, okay, if A is L, we say L infinity morphism is a quasi-isomorphism is F1, which was cochain map, okay, is a quasi-isomorphism, is a cochain complex. That is L infinity morphism. So before I go on further, to say anything about quantum, this is all classical. And I want to say this is exactly just classical physics. I just did classical physics. In the following sense. So let's consider a product. Okay, we have product. So instead of dj array, let's consider dj being in the picture. So then the point is following. We know if there's no product, we know in the cohomology of cochain complex, we have cochain complex with zero differential. Okay? Then you can ask the following question. What will happen to the cohomology of dga? Okay? Answer is, obviously, is an A infinity algebra. Okay? So on cohomology of dga, there will exist something called minimal A infinity algebra. Which is quasi-isomorphic to dj at the chain level regarded as an A infinity algebra. Okay, this is well-known theorem here. So that's why, those reason is why. So if you start from cochain complex, on cohomology we just have cochain complex with zero differential. But if you start from dga, cochain complex together with compatible with product, if you go to cohomology, we have more than dga. Okay? We have something called A infinity structure. So what is A infinity structure? And I will just tell you what it is. Okay? So product is just let's, instead of writing product by this, let's denote this M2. M2 is a map from B tensor 2 to B. Okay? And with some degree 0. And of course, we have differential is D to V. Okay? So let's just make up M3, invent something to all those higher product. V. Okay? Of course, such that D squared equals 0. Okay? And D is derivation of M2. AB equal to M2 A dA comma B plus M2 A comma dB plus minus, okay, derivation of product, but M2 then we want to consider whether that is associative. If this guy is 0, it will be just associative algebra. Just the differential graded algebra that we know. But this guy is not 0, but defined of two homotopy. So it's there's some M3 ABC plus M3 DABC, M3 ADBC. It's obvious what I'm doing, but I'm going to finish it. Anyway, DC, etc. Okay? So associativity is violated up to homotopy. So if you go to homology, D vanishes, so this thing all vanishes. So it's a kind of natural homotopy notion, relaxing associativity. Then you also need some coherent condition for M3 and M2 being satisfied. Okay? So that kind of thing, you feed it up, that is A infinity algebra. Okay? And that is actually, you can give a definition as a co-derivation, co-derivation of tensor algebra of B, which is scaled to 0, and so on. Okay? There's some relation. It doesn't matter. I mean, what the detail is doesn't matter down here. Then we say, so let's say A infinity algebra by M. So we have D, M2, M3, etc. And obviously, if M3 and higher all vanishes, A infinity algebra is nothing but just DGA. Okay? Differential graded algebra. Differential with the product. So if this is an A infinity algebra, we say minimal A infinity algebra. It's just A infinity algebra with zero differential. Okay? They call it minimal. Okay? Here. So that this zero.
So what do you mean this is classical physics?
No, I'm going to say why this is classical physics. Okay. But I have to finish this.
After you said that,
oh, sorry. I'm sorry. Yeah, I have to finish this.
Yeah. Algebra,
yeah. I have to finish this, and then I will really go back to classical physics. On here. So this theorem kind of says, okay, on cohomology of differential graded algebra, we have minimal A infinity algebra structure, which is quasi-isomorphic to the chain level as an A infinity algebra. And of course, it should be minimal, right? Because the cohomology vanishes. Okay. Now, so we have differential equals 0, but we have M bar on cohomology, which is 0 and some M2, etc. Okay? We have this structure here. Now, basically, those M2 is just ordinary product, the cohomology ring, and M3 is massive product, and M4 is like those higher massive product, and so on. Okay? Then, if you do this thing again, basically, you can construct some map H tensor N to K. Not just H. Okay? From H to K was this just map. From H tensor N to K. So some multilinear map to the K around here. But this is nothing but just the resulting map is nothing but just the composition of this original map from original way of computing homotopy invariant together with just this algebraic structure. Okay? M2. Okay? So that is kind of we can also define multilinear map around here. So basically, if you start from DGA, okay, to figure out complete homotopy invariant, you have to construct all this thing and find the quasi-isomorphism as A infinity algebra, okay? Then use this cycle, this cochain map C, okay, to produce number that will characterize. They are the homotopy invariant of this A infinity structure, if you want to say, yeah. And it's actually more than that because, as I don't mentioned, if C is non-degenerated, okay, this introduces some pairing on the homology by integration, okay. It's just this was product, but this will be H2 would be just the pairing down here, so that will give some inner product here. Now, of course, we have M3, M4. So we have some kind of homotopy inner product as well on the cohomology. Okay, so we have to describe all these things, but this is nothing but doing this. Whatever you do, that's what you get. So any questions so far?
So what does this numbers mean? What is this numbers describing?
Sometimes it will be, depending on the situation, sometimes it will be like period. The period. Like period. In mathematics, like period. Like,
no, what I mean is you got a bunch of this,
actually.
Right? So
that will be all homotopy invariant.
you mean this CN? I mean,
for example, like Euler characteristic is homotopy invariant.
Your original C, of course, that's just from H to K. That's just like you said, it's some integration on a cycle, right? And then this higher one, how do you interpret them, or do you want to interpret them, or you don't care?
No, actually, you don't need to interpret them because it's just the Poincare pairing. So we have differential form cohomology class H. represented by some closed differential form, alpha, and there's another, then we'll take wedge product and integrate over cycle. Okay, that will introduce Poincare fairing. Okay, but that whole thing would be like just defined from map from H to K together with the algebra structure on H.
Okay.
So that's something that we are doing usually. Okay, usual thing, like those cohomology ring, Poincare fairing, and all those things. It's just this here. So this is just the standard mathematics. Now I'm going to claim that this is standard physics, standard classical physics. Classical field theory, yeah.
Field theory.
Yeah, with classical, like just the classical physics, whatever it means. Yeah. Of course, we can. Let me just make one more remark. I'm sorry. Yeah. We can change this thing to Lie bracket. Okay. Then we'll have minimal L infinity algebra, Gaussian isomorphic, whatever. Then we'll. Then in this construction, we see will produce invariant metric, like, you know, the usual thing that, you know, product something like that. Okay, this kind of thing will also come from that kind of construction, and some homotopy version of this would also appear. Some infinite inner product, some Frobenius infinity structure. The kind of all those things just appear in this way. Okay, now I'm claiming why this is classical physics. Like here. So let me give the simplest possible classical field theory. I'm doing this because all the example is just complicated. Okay? Simplest possible classical physics field theory. Here, you can regard this model as a zero-dimensional classical field theory. So usual mechanic is 0+1-dimensional classical physics, mechanic. So so here physicists will say n plus. When I say 0+0, means my space dimension is 0 and time dimension is 0. So I don't have time, I don't have space. Okay, not at all. Okay, 0+1 dimension is just if particle is 0-dimensional object and move in time. Okay, so the trajectory would be like 1-dimensional. I'll call it 0+1 dimension theory. And string theory would be 1+1-dimensional quantum field theory. Okay, Yang-Mills theory would be 3+1-dimensional quantum field theory. So classical quantum field theory. So I'm going to talk about 0+0-dimensional case. Okay, so imagine some 0+0-dimensional space field theory is actually described by map from point, which is my 0+0 dimension, to some target space M. Right? Agreed? Is it physics? Is it physics enough?
Physics have time, so this doesn't look physics. But anyway,
even simpler than physics. String theory will be I have a Riemann surface, okay, string moving in M. So this is 1+1 dimensional thing here, okay. So I'm going to even consider this. Why I'm doing this? Because I will have to, if I do this example, then I have to consider space of all map. Then I will have to construct the space of all functions on the space of all maps, and so on. Okay, then I will have huge whatever analytic, whatever difficulty it has. I have unnecessary technical complication. Okay, so here space of all map from point to M is just M itself. So space of all functions on space of all map is just the space of functions on M. Okay? And I want this to be smooth. I mean, it doesn't need to be smooth, but to avoid any possible problem, let's just consider C infinity functions on M. Here. Then pick a function as Cm. And I will declare this class collection. Or other model would be just a polynomial algebra, okay? So affine coordinate ring, affine n space. That, okay, if you want to this way. So anyway, either this or in this, let me call that as a classical action. Okay. So if I put the suitable coordinate, okay, so let me try to be explicit. This is a function here. Then let's take derivative. Let's choose some local coordinate, x1 to xn, whatever, and xi derivative equals 0. So this is just the critical point of this function for all I. Let me use capital I. Just I is 1 to n. This equation I'll call classical equation of motion. Okay? This is just the stationary point of this function. Okay? So because I'm doing 0 for 0-dimensional series, I don't even need to variational calculus. If you do 0 for 1 dimension, you have to do variational calculus. And this is my Euler-Lagrange equation. Okay, so we are talking about physics. Extremely simple physics around here. Now, classical physicists to say that if you can find the solution space of this guy, classical equation motion, is done. Because classical physics is completely dictated by classical equation of motion. Okay? So let's imagine some space where this really stubborn classical physicist living. So he was based on this equation of motion. So let's call it classical equation motion space. Classical equation motion space is something the classical observer live down here. Now, whatever happened, whatever thing here, so let's say some x, this is classical equation motion space. Now the point is, in the end, this classical equation motion space, even if this simple case would not be just ordinary space, okay, it should be kind of derived space actually. It is not really anyway. So classical equation motion space. Then, according to classical physics, anything classical observer would be just a function from classical equation motion space to, when if this real number, that would be observation. So observable, classical observable, okay, it's just the functions on classical equation of motion space, okay, and it will form an algebra. So we will have a classical observable form of algebra of classical observable. So we want to describe algebra of classical observable. Okay, then we are done. Okay, you characterize every observable and you know how they are related, then we are done. So this classical physics is finished with this thing here. So how we describe this? Of course, what you have to do is following. Instead of solving this equation, let's do something in an off-shell way. So let's just consider all functions of polynomials, okay? And then if I have two functions, O prime, and another function O from original space, ambient space, which difference is 0 modulo classical equation of motion, okay? then classical observer would regard them as identical thing. Okay?
So what this is a function on M?
Yeah, function on M. O and O prime.
What do you mean by their differences equal to 0 modular class equation, whatever? What do you mean by that?
I mean by that,
Yeah, what do you mean by that?
if O difference O prime minus O vanishes on classical equation motion space. That's what I mean by that. Okay. So in other words, this is something like if I can write down this something as summation, some functions, because I already put local coordinate, like partial xi, partial s classical, okay? Then this thing vanishes by classical equation of motion. Or if it was this is nothing but algebra of classical observable is nothing but okay, O polynomial modulo ideal generated by Jacobian. So it's a Jacobian ideal of S, CL. That's what I mean by it. Here. So this would be algebra of classical observable. So I call this on-shell fixture. On-shell fixture is this thing, okay? And off-shell fixture is this whole thing together with some distinguished function. That is off-shell fixture. Perhaps in this field, I'm never able to say anything about quantum. Anyway. Okay, now let me stick to this model because this is even simpler than working with C-infinite functions, okay? Polynomial, okay? I would really want to construct a simple model. This is, of course, the module, quotient module over here. Now, sometimes, okay, let's consider this equation. Okay, here, these are all polynomials, okay? So, if you consider this description here, that this equation has an ambiguity. What kind of ambiguity we have? If I assume that I have some polynomials, sequence of polynomials, Ri, such satisfying the relation that partial xi, partial scl equal to 0. Assume that I have such a polynomial, Ri, here. Then I have that lambda there. Let me define lambda prime I to be just lambda I plus Ri, this polynomial. Okay, then I also solve this equation. Okay, so here, this lambda is defined, ill-defined, okay, modulo something like that. But if you look at this is nothing but the symmetry of classical action. This is symmetry vector of classical action. What is symmetry in terms of physics? Is that, okay, I have action functional in terms of original variable, but now I change that thing to xi to xi. So I have original thing. Okay, I act some on my space of classical field. I have some action of some group, something like group. Okay, which infinitesimal action is something like R, like I. Okay. And this would be expanded as Sxi plus epsilon, Ri partial xi partial s, and some higher version, okay? So this is nothing but, this vector is nothing but if there's some group is acting on this space of classical field, then this Ri is nothing but just a representation, vector which generates action around here. So this is equal to 0. Okay, so I'm talking about infinitesimal symmetry. So it means that action has some gauge symmetry on here. Okay? Is that clear so far?
Wait, what do you mean by gauge? I mean, clearly if you have some symmetry, you look like this.
Yeah. It looked like this. But I'm going to say this is what physicists call gauge symmetry.
Oh, okay. So you're
Yeah.
saying this kind of diffeomorphism is going to be keeping the action function
Invariant. Yeah, yeah,
in that sense.
yeah. Now, so symmetry is a problem. So if you consider, so let me write down this in some naive way. Assume that I have a symmetry vector. I will denote vector in this way, symmetry vector. I have identified vector with derivation. And another symmetry vector. Okay, so I'm not going to write down this here. So if we have this symmetry, then we can guess actually our physicist friend is not really living in the strict classical equation of motion space defined by this, but also there is a group is acting on this space, and it must live in the part which is invariant under the space. Okay? So you can imagine the classical equation of motion space is actually certain space which algebra function and the space is given by some invariant part of this quotient. Okay? Now, but the symmetry, when you take symmetry vector here, that is defined in the whole space. But we have to also worry about whether our classical friend would recognize one symmetry to other, difference between them. If the difference between two vector fields vanishes by equation of motion, you would not able to distinguish them. Right? If this is can be written as something like lambda ij of something like partial xi, partial scl, also partial xj, partial. I'm sorry I'm using physicist notation, but this element just completely elementary, so I don't need.
What you saying?
So we know some symmetry is acting on the whole space, but the issue is that what kind of the symmetry acting on the equation motion space, where classical equation motion vanishes. So if you have a two symmetry, which difference vanishes by equation of motion,
Then they are the same.
they are the same
On shell.
on shell.
Okay.
They are same in the on shell. So we actually not just considering this equation, but the equivalence class of that equation. Okay, here we are already taking an equivalence class. But now this lambda, this thing, of course, also ill-defined. Because we can imagine changing some lambda to something else, okay, that would be automatically 0. So we have to go on, okay, and you figure out every possible relation that this thing would have, okay? Then we can...
Why do you want to figure out all these relations?
Because we want to figure out...
Right? What do you want to figure out?
We want to figure out where classical physics live.
Okay.
First, we know equation of motion should be satisfied. So it must be space where algebra function is this,
Yes.
this quotient ring, okay? And then we notice that sometimes they may have non-trivial symmetry,
Right.
okay? Then we know, then it must group some symmetries acting on that space.
So you live in a quotient.
So living in the quotient by invariant part.
Right. So well, that seems to be already answered the question. So why do you keep going with it?
But the thing is that we have this motivation because this thing was ill-defined. That's why you get the symmetry came from redundancy. This lambda is, someone give O and O prime. This is ideal membership problem, if you want to say in that way. But this guy is there's a redundancy. Gauge symmetry is redundancy.
Yeah.
No, symmetry is. So, but if you consider this to figure out when two gauge symmetry is equivalent. Then we have to determine what is lambda ij, but that has also redundancy. Okay, so we have redundancy and redundancy and redundancy. So you should able to, you want to describe all possible redundancies. And if you can do everything, all possible redundancies, then now you can kind of confidently say, oh, this guy must living in this space, if you can deal with the redundancy on here. Okay, now following is obvious. Let me write down, let me make a notation. Assume that I have some class of that thing. Okay, so summation I, let's say this is like vector R alpha, like that. So this is some arbitrary index by working out the equivalence classes. Assume that that class is right, indexed by alpha. Okay? Oh, yeah, so indexed by alpha. So then let's consider corresponding, and this is a vector, so let's consider corresponding derivation. Okay? Derivative. Then we know that we have Lie bracket. Okay? Commutator of derivation is derivation, but if this was generating set, maybe written in this way, no way, because commutator of symmetry is also symmetry. And if it's finitely generated, we should be able to write this down in this way. But we already know that what you are dealing is the symmetry modulo equation of motion. Okay? So we'll actually, in general, will not get this strict relation, but which term vanishes? Modulo classical equation of motion. Okay, so that's the part here. The claim.
It looks like more complicated than, say, the more straightforward A-infinity algebra. Right?
It's actually much more complicated than A-infinity, much more complicated than L-infinity. We have to consider A-infinity and L-infinity together as two different limit of more higher.
Your algebra, I mean, your algebra first modular Jacobi idea,
Yeah.
then you like when you do something else, and then something. So is that process? I mean, that's not the process of infinite algebra, right? Is that?
No, here actually we are. I mean, it will be process. I cannot. Point is, I mean, not the point. Point is. Actually, it is even not possible for me to describe classical physics within 1 hour. So I'm just telling you just one section of classical physics. Yeah.
I see.
Just so I'm going to the L infinity direction only. L infinity direction only. So here. Now, if it was not modulo classical equation of motion, you recognize some Lie algebra here. Okay? So then what is the acting? Okay, you integrate like Lie algebra, then you get some Lie group. So you say, oh, group is acting. So what is my classical equation print living? He must living in the part G invariant. Which algebra function is the G invariant part of this? Okay? So actually in this case we know the answer. He must living in the GIT quotient. Okay? But if this is not strictly this, but there's some non-trivial part here, which give higher part as some another non-trivial thing, okay, then it's actually not Lie algebra. So it is Lie algebra only up to homotopy. Okay, so if you imagine group, so you have to imagine something like Lie group up to homotopy or something. Then, did you even heard about homotopy Lie group GIT quotient?
I suppose there must exist such thing.
Yeah, such a thing must exist, okay? But that is not even, okay, clear how to describe it. Usually, in the physics problem, it is just Lie algebra. SU2, SU3. Okay, that's why we just use all those that thing around here. Okay. Now, the point is that this relation I'm just describing of modular equation of motion is exactly up to homotopy. So we can just make a simple model for that. How do you make a model? Yeah. Basically, if you start from polynomial as a classical thing, we have some action function around here. So somehow we need to consider like vector field, not just vector, not just the polynomial, but some vectors and bivectors and so on. Okay? So let's just extend this thing to introducing some other variable, eta. Okay? Some polynomial algebra, but here in this case now, eta would be known is not symmetric. It's anti-commuting. So just into some anti-commuting, so some graded polynomial, and x and eta is commuting. Etc. Okay? Then this thing, and let's introduce degree. Just assign everything here to degree 0 and assign everything here degree -1, okay, for my convenience. Okay? Then I can decompose this one into b minus n plus, go to up, b minus 1 plus b0 by degree. And it stops at -1 because this thing is anti-commuting. The b0 is my original polynomial algebra. Okay? That's B0. Because B0 has no eta in there. Okay, so I here. Then also we notice that, I made a copy of x by eta, so we can introduce natural pairing. So I will introduce bracket, my bracket xj. I said it's 0. I'm undoing Poisson bracket. Eta I xj is Kronecker delta ij, and eta I, eta j is 0. And you can has that. It has symplectic structure. So you just introduce a bracket between two there here. Then extend this thing as a derivation of product. Because I'm only doing with the generator. So in this sense, so let me call this B without any index, okay? B and the bracket homograded Lie algebra. Can easily check this. So I obtained the grade Lie algebra for free, okay? And the degree of this thing is degree 1, right? Because eta is degree -1, x is degree 0. It becomes number, so it's degree 1. I have degree 1 bracket in here. Then,
Wait, so does this have physical meaning too?
yeah.
Is that easy to understand? The eta.
Eta is called, okay, do you want a name? This class field. This is classical field. This guy called anti-classical field.
What is this anti-classical field? Antimatter stuff or something
No.
else?
No, it's not antimatter. Antimatter would be also classical field.
Okay.
Yeah.
So
There will be antimatter if you want.
Do we observe them in nature? I mean, are they
No. I mean, you see, I mean, that's really exactly, I'm really telling you, you will see if I just listen to this, okay? Physics, even classical physicists already derived it. Classical physics dealing with the derived mathematical structure.
It's very, kind of maybe very naive. No, I mean, some of the classical field, like you're looking in the nature, like photon or something. But this anti-classical field, are we also looking for?
No.
They do
No,
not
it's like
exist in nature.
they do not exist in nature.
Oh, okay.
Or whatever nature means, it depends on how you define nature. But to describe nature, you need anti-saying, whatever, to describe correctly. So we have a bracket around here. Then it's clear.
So my question is, why do you need anti-thing to describe the nature? Is there a simple reason for it?
Because simple reason is following. So here, so before I introducing this, I told you what to do, what we have to do to understand classical physics. To understand classical physics, you have to figure out all those equivalence relation, symmetry up to homotopy. You have to relate that here. I'm just tidying that up. I'm just saying that modular equation of motion is exactly up to homotopy. So I want to give some homotopical interpretation of this. That is the device I'm cooking up. I'm cooking up something to refit this story.
Oh, so you're going to make this better. Okay,
yeah, I just want to make this better. Yeah, exactly. And here, then S depends only on X, so it is obvious this is true. Right? Because bracket vanishes degree 0 here. So let's define Q, some differential, by bracketing it as CL. Then Jacobi identity tells you, then this thing extend degree I to degree I plus 1.
This is not what you call ghost, right?
This is not ghost.
Okay.
This is classical field
Anti-classical.
and anti-field of classical field. Okay.
Anyway.
I don't even have a ghost.
Okay, don't worry about it. I'm just trying to understand.
Okay, yeah. Because you asked me, so this I'm going to this direction, okay? Then QCL square equals 0 using Jacobi identity. You can also prove that Q is derivation of bracket using Jacobi identity. So if someone give you action, so classical field plus classical action allow us to construct a differential graded Lie algebra. Of course, we also have product. I mean, this is like space of polynomial functions. So actually, we also have product. Okay, and the Q is derivation of product as well. So we also have differential graded algebra, not just Lie algebra. And also bracket is derivation of product. So what you actually have is differential Gerstenhaber algebra. So that is free construction, okay? So let's forget about product. Why down here? Now, what is Q? I told you QCL was bracketing with SCL, but X is only defined by X, depend only on X, original variable, but only non-trivial commutator is coming from eta and X, and we are dealing with polynomial and so on. So you can write down this as taking derivative of xi partial SCL and taking derivative of eta I and sum I together. Okay? Here means this operation kill eta I, but extended as a derivation. So this is my QCL. Now, because I have a complex already, so let's try to compute cohomology, degree 0 part. Everything is kernel, but what is image? Anything of degree -1 would be written as something like lambda I x eta I, right? Everything would be like this, degree -1. So then you compute the QCL lambda, then you have this trivial lambda I x partial xi partial SCL. Okay? So exactly something which is image of Q is just the ideal generated by classical equation of motion. So this is exactly Jacobian ideal generated by this. Okay, so we're dealing with cohomology. Then what is -1? This is symmetry modulo equivalence. And what is -2? This is symmetry of symmetry, redundancy of redundancy. Oh, wow, we're just doing homological algebra. Okay, so that, okay. So then, because we have the bracket here, we already know. So here, basically, this picture tells you our friend actually living in homology. Okay? Homology, because there where, in homology, it's really just defined. Oh, why it is. This was summation. On homology, Q vanishes. Sorry. Equation motion space vanishes. So condition QCL equals 0 is just exactly the on shell. So he's living in the homology. Now, we know this is an algebra. We know this is a Lie algebra. It's strictly here. Then we also know this Lie algebra is the module of this algebra, and this algebra is module of that thing, and so on. So there are many, literally, and if you just consider this part only, actually what you have is you have groupoid structure. Groupoid. Yeah, Lie groupoid. Yeah, in this case it's Lie. So if everything vanishes, I mean, every other thing vanishes, then you just have Lie groupoid structure here. Something like that, okay? But if it does not vanishes, okay, then we may have a problem, but we can just invent name, okay? So you may have some homotopy version of groupoid, whatever it is. Or we already know that in the cohomology of this thing, we have homotopy L infinity algebra, minimal L infinity algebra. Okay? So minimal L infinity algebra structure is nearly, in that case, it's just the structure living on something that my classical physicists would be very, very familiar. Okay. They may have also minimal A infinity structure because we have associative product here. But bracket was derivation of product. So there's a relation between bracket and product. So that relation will also generate homotopy relation. So you may say actually on your classical friend, okay, he is living with homotopy Gerstenhaber algebra. So sometimes they call it G infinity algebra. Whatever it means, some homotopy version of it will be there. Okay, describing all those things would be classical physics. Okay, now.
Yeah, then we also have quantum physics, right? So.
Quantum physics is it's much more. I don't have time to describe quantum physics, but doing classical physics in this way seems to be already quite enough because usually we don't have more structure. So let me return to this example here. Assume that in this example, assume that HCl is just H0. Cl, okay? Then we build this. We have B0, then I have QCl, and B minus 1, I have QCl, etc. Here. Then here I have this quotient module. Okay, and let's regard this as chain complex with zero differential and so on. Okay, then by taking cohomology, I have this map, and these two cochain complex are quasi-isomorphic. Okay, so what I've just described without Lie algebra structure, if we forget about Lie algebra structure and product, this is nothing but the resolution of here. So because there are non-trivial relation, this is resolution, okay? But if HCl is more than H0Cl, then this would not be quasi-isomorphic, right? Because there will be non-trivial cohomology. Then actually we have to enhance this such that it is quasi-isomorphic to this guy. And how we do that? Unnecessary cohomology should be killed. How do they kill that? Okay, way of killing it, I mean, make it defunct is to make it as a friend, you know. So killing it means to actually introduce as many new generator, new variable, freedom, as many of your cohomology. So if there's a cohomology class of H-1 cohomology class, you introduce new variable. Okay? Dual to that, such that dual variable to extend the space, extend this complex, and extend the Q such that heavier. So if only H is H plus H minus Cl, okay, then newly extended variable would be called ghost. That's why Gage-Smith is ghost. Okay, and introducing ghost and changing this Q is nothing but, you have mathematical name for this. This is nothing but Kosu-Tate resolution. In this simple case, what he just did is Kosu-Tate resolution. If we forget about the bracket and the product. So, basically, what classical physics is Kosu-Tate resolution enhanced by G-infinity quasi-isomorphism. So, Kosu-Tate resolution enhanced by G-infinity structure. Probably hard problem to do this.
Why is that problem hard?
I think even polynomial case is hard enough, actually.
Right. Isn't that just
well, I didn't even define what is Kosu-Tate resolution enhanced by G-infinity structure.
Well, your physicists, they can always imagine there is one. And they can always integrate in infinite space. They wouldn't have trouble.
Yeah, so because so here, basically I'm kind of, okay, so then what is that, he is living in some space. What is my classical equation motion? Where is the place that my classical friend live? So he's living in some geometrical version of that algebraic structure. So that is where classical physics is occur, and we are supposed to be governed by classical physics. Then we are actually living in that space which is governed by that kind of algebraic structure around here. So that's, for example, where you are. Okay, but the point, I just want to say one thing about quantum physics. Okay, then I will stop. Okay, one thing is, the important thing is that we have notion of classical limit. Okay, so if quantum theory, we have notion of classical limit. Classical limit, we forget the structure, quantum structure. Okay, so if we study classical physics and say, well, if this is conclusion, okay, we have to actually doubt this because we are talking about not just classical physics alone, but we should have classical physics which is appear as a classical limit of quantum physics. So not every classical notion which looks natural in the classical physics viewpoint would be valid. Okay? We just need to only those notions which can be lifted coherently to the quantum world. Okay? So, in that sense, we actually are not living in this space because this is actually wrong. Yeah. You can say, I mean, if I give really crude analogy, you can say this is really like you are doing drum theory without knowing Hutch theory. Okay, then we don't have notion of harmonic form, etc. Okay, so then every representative of cohomology class would be treated equally. Okay? But there's additional structure like Riemannian metric tells you there are really unique and very nice representative called Hodge harmonic form. So the role of quantum thing, okay, if I like in this say crude way, is doing some kind of Hodge theory. Among all those, like if a classical thing is G infinity so on, most of this thing is like, okay, they don't care. Okay, there's something which what I'm saying is that if this is true, then we have to compare. We have to say two classical physics is equivalent, classical physical equivalent, if there is a G infinity quasi-isomorphism. Okay, but of course G infinity, there could be many G infinity quasi-isomorphism up to homotopy and so on. But quantum physics tell you that okay, no. We don't care about all G infinity quasi-isomorphism. We only care about particular one. Very special one. Yeah. Very special one. Like, analogy is like when you do mirror map, okay? You just not just invert mirror map anywhere. You kind of, in the complex moduli space, or in the some you go to some special maximal degeneration, then you introduce some affine coordinate system. There you do the mirror map. Okay, so they give some additional structure given here, such that, so it gives a unique representative, kind of good representative like harmonic form right here. So when you compare to physics, quantum physics, you only need to compare those good one. Okay? Then it follows that they're derived equivalent. So idea of derived thing is that we regard everything equivalent. So let's compare totality of A with the totality of B. Okay? But quantum physics let us say, okay, but there's a really unique quantum representative. You only need to compare these two. If they are same, okay, we are dealing with the same physics. But then actually that also implies derived equivalence. So in that sense, quantum physics is already derived. I'm sorry that I couldn't tell you anything about quantum thing. Actually, I never succeeded in going there. I actually never ever give a talk about quantum thing. And beside from my class, our own class, I mean, anyway, so yeah, so
all right.
Yeah,
So
that's it.
Yeah, so we some speaker give us a very insightful look into quantum science. Okay, so we
Thank you very much.